back to this image again, this image that the Hubble Space Telescope took. And now I'm going to go into the importance of an image like this. Zooming in on one of the galaxies because it's a nice spiral galaxy. And what you can see here is even for these galaxies that can be pretty far away from us, this galaxy, I don't know off the top of my head, but it's something like 6 or 7 billion light years away, we can still see spiral structure. Well, what's the importance of this? Well, light has a time that it takes to travel. It has a finite speed. So in a galaxy that's far away, the light that travels to us that we detect has been taken a long time to travel to us. If we see a galaxy that's 7 billion light years away, the light has taken 7 billion years to get here so that we can now see it. So when we observe a galaxy like this that could be 7 billion light years away, we see it as it was 7 billion years ago. Which means that we can compare galaxies 7 billion light years away, 10 billion light years away, 5 billion light years away to the galaxies right here on our doorstep. And we can get an idea of how they're changing over time, how they evolve with time. So if we can detect spiral structure in these galaxies that are very far away, from the spiral structure now, we should be able to determine the mass of the black hole in the center and how centrally concentrated the dark matter is with time. And we can test how both of those things evolve over time as well. What we expect is for the dark matter to become more centrally concentrated and for the black holes to get bigger over time as they get closer to us. Why do we expect that? Well, the black holes will be swallowing material. Once something falls into a black hole, it can't escape. So therefore, you expect black holes to become more massive over time. It's a slow process, but over the periods of billions of years, you should see an effect. One other thing that can happen is that galaxies can actually merge together, and if all these galaxies have black holes in the centers, when they merge together, eventually the two black holes will merge and form a black hole that might be twice as big. So that would show a more sudden increase in the black hole mass. If they're just slowly swallowing material, that will show a more gradual increase in the mass of the central black hole. Now, I just want to take a little bit of time to show you some telescopes that I've actually used to actually pursue my research. This telescope here, this is the 2.5 meter DuPont telescope, and it's in Chile. It's on a mountain called Las Campanas. And I think for about 3 years of my life, I probably spent something like 70 or 80 nights here just collecting data of galaxies, images of galaxies. This is the same mountain, and the next stage of that same project, actually, where I collected all those images of galaxies, is to get the spectroscopy from this telescope right here. So remember, the spectroscopy will tell you how fast the stars are moving around the centers of those galaxies. And these are the little dorms here. These are the dorm rooms where astronomers sleep. And of course, they sleep during the day. So they have nice blackout windows on them as well. Here's a little close-up of the DuPont telescope with this little gold car that they give you to drive around on the mountaintop when you're observing. This is what the telescope actually looks like inside the dome. Astronomers paint their telescopes all kinds of strange colors like yellow and blue. But this is generally, most telescopes actually look like this when you get up close to them. Obviously, they change, the size is different from one telescope to the next. This is what we consider probably a relatively small telescope these days, 2.5 meters. Those other telescopes that I showed you before, the ones in the background with the domes, they are 6.5 meter telescopes. So that's getting up to large telescopes these days. Large telescopes are really in the 8 to 10 meter range these days. And these are some of the images that I've taken with that telescope. But here's a galaxy that has fairly tightly wound spirals, I would say, so you would expect quite a big black hole in the center, quite a massive black hole, and also a very sharply peaked dark matter in the center. You would expect quite a lot of dark matter for this galaxy, for it to be very centrally concentrated. Now this galaxy, it's kind of a little bit more difficult to tell how tightly wound the spiral arms are, but I'm just putting this in there to show you how pretty these galaxies can actually be. Here's another galaxy which has probably more open wound spirals than the first one that I showed you. So it would have a lower mass black hole, and the dark matter would not be as centrally concentrated as it was in the first case. Now this is another spiral galaxy as well, except we're looking edge on at the disk, so we can't actually see the spiral structure. And just one more image of a galaxy here. This is actually two galaxies in the process of merging. I said just a few minutes ago that we know that galaxies merge. Well, here's an example of this. This is actually the closest example to the Milky Way of two galaxies that are in the process of merging. They haven't finished merging yet. This is the center of one galaxy. This is the center of the other. Now, if you had a really nice image of this galaxy, a really deep image, as astronomers would say, you would see two tails, one coming off here and one coming off here, two antennae, because these galaxies are called the antennae galaxies. You can't really see that well in this image. So if this is the center of one galaxy and this is the center of the other, you would expect to find black holes there. Indeed, there are black holes there. We can't see them directly, but what we can see is the effect of the material falling into those black holes. These two black holes are actively swallowing material. What happens as black holes swallow, at least if they're swallowing a lot of material as they are in this case, that material falls into a disk as it rotates around the black hole. That disk can become extremely hot, so it starts to glow. It gets so hot that it emits X-rays, and it emits a lot of visible light as well. And that's one way of detecting black holes in the universe. And that's probably the most significant way in which black holes can grow over time as well as merging. And I just put on some logos here. This is the Arkansas Galaxy Evolution Survey, which I mentioned a little earlier. Another project I'm involved in is the Carnegie Irvine Nearby Galaxies Survey. And that's a survey of the 600 brightest galaxies in the southern sky. And our funding has come from the Arkansas Space Grant Consortium and the Arkansas NASA EPSCoR program as well. And I just wanted to finish with some accomplishments in 2008. Our main accomplishment was really this discovery of the relationship between supermassive black holes and the centers of galaxies and how tightly wound the arms are. And this actually got a lot of press. I had an interview with the BBC. There was an article in National Geographic, Astronomy magazine, Sky and Telescope, and also USA Today, amongst some others. And that's all I had to say. Thank you.